this video, we'll take a look at a second example of a hypothesis test involving a population mean. This example, again, is similar to section 10.3, exercises 13 to 18 and 21 to 24. The standard car air fresheners produced by Dashboard Delights has a mean lifetime of 36.1 days, meaning that the standard car air fresheners release odorizing molecules for, on average, 36.1 days. Engineers at Dashboard Delights recently designed an extra-strength car air freshener which they hoped would last longer, on average, than the standard car air fresheners. To test this new result, the engineers collected a random sample of 101 extra-strength car air fresheners, measured their lifetimes, and calculated the sample mean lifetime to be 36.9 days, with a sample standard deviation of 4.2 days. Is there sufficient evidence to conclude that the mean lifetime of extra-strength car air fresheners is greater than the mean lifetime of standard car air fresheners? Use an alpha of 0.05 level of significance. So our first step is to summarize the information and identify the point estimate. In this study, they're comparing two different air fresheners, the standard air freshener and the extra strength air freshener. And it's known that for standard air fresheners, the mean lifetime is 36.1 days. For the extra strength air fresheners, the population mean is not known, but the engineers did take a sample of 101 extra strength air fresheners and observed their lifetimes. And they found that the sample mean was 36.9 days and the sample standard deviation was 4.2 days. So these results seem to indicate that the extra strength air fresheners are lasting longer on average than the standard air fresheners. The extra strength air fresheners had a sample mean of 36.9 days, and that is greater than the mean lifetime of the standard air fresheners, which was 36.1 days. However, we will still need to test whether this sample mean lifetime of extra strength car air fresheners, 36.9 days, is significantly greater and therefore sufficient to conclude that extra strength air fresheners indeed last longer. So step one is to state the hypotheses. For this hypothesis test, this is involving a population mean, and that means again that we'll use mu to represent population mean. And in particular, remember that mu is always the unknown of the hypothesis test. And the unknown in this case is the population mean lifetime of the extra strength car air fresheners. The sample mean is known. That was taken from the sample, but the population mean is unknown. So here are the hypotheses. The null hypothesis is always that there's no difference or no change, and you'll always see an equal to here. So the null hypothesis is that the population mean of extra strength fresheners is just the same as the population mean of the standard air fresheners. The alternative hypothesis has to do with the question that the engineers are asking. And in particular, I highlighted in this description that they wanted to know whether the extra strength air fresheners would last longer than the standard air fresheners. So lasting longer, that's another way of saying that, is they want to know, is the lifetime of the extra strength air fresheners greater than the lifetime of the standard air fresheners? And so in the alternative hypothesis will use greater than. So the population mean lifetime of extra strength fresheners is greater than the population mean lifetime of standard air fresheners. And again, on the notes, I have written these hypotheses in full sentences, just for clarity, but on a homework or test or your research, you don't necessarily have to write full sentences like this. These symbols are what you would usually write for your hypotheses. Step 2 would be to verify the requirements for this hypothesis test. So again, one requirement is that the sample must be a random sample, and in the description it does mention that the engineers took a random sample. Another requirement is to meet the normality condition. In this problem, it's not mentioned whether or not the population is normally distributed, but it doesn't really matter because they're taking a very large sample size. It's definitely more than 30. And so regardless of whether the population is normal, this condition, that our sample size is more than 30, is good enough to satisfy the normality condition. And then the third requirement is to make sure that the trials are in effect independent. And to verify that, we could use this inequality that the sample size has to be less than 5% of the population size. I won't go into detail here, it's described in the lecture notes, but it's similar to the previous example of when we checked that third requirement. But we'll go right on to step 3, test the hypotheses. We'll take a look at the first approach. So one approach would be the classical or the test statistic approach. And the first thing that you want to do is sketch out a t-distribution curve and then use table 7 to find the cutoff t-value for the region of the curve that would represent unusual outcomes. Make a note that this is a right-tail test because our alternative hypothesis was for greater than. Also, alpha is 0.05, and that's going to be the area under the right tail of the curve. And it's drawn out right here. There's the area of the right tail. We'll go to table 7 and look up what this critical t-value, this cutoff, would be. Remember that when you use table 7, you'll need the degrees of freedom and the area under the tail. The degrees of freedom in this case would be n minus 1. That's 101 minus 1, which is 100. The area under the right tail is 0.05. That's the alpha. We can go to table 7. Here's an alpha of 0.05 for the area under the tail. Here's the degrees of freedom. It's going to be 100, which is way down here. And let's see. We'll follow this down. Here's the down here, all the way down to 100 degrees of freedom. Here's 100 degrees of freedom. It looks like they're lining up at 1.660. So that is the value of our cutoff t-value. Remember that table 7 gives you the t cutoff values for the right tail of the t curve. And that's exactly what we wanted. This is a right tail test. So that 1.600 is in fact the right cutoff, the cutoff that we're looking for. The next thing is to calculate the test statistic. Use that formula. Put in all the values into that formula. The population mean of the null hypothesis, the sample mean, standard deviation, the sample size, and it comes out to 1.9143. The last thing is to determine whether this test statistic is inside or outside of the critical tail. And in these notes, there are reminders about what it would mean in each case, whether it's inside or outside the tail. And looking at this, 1.9143 is inside that critical tail. It's somewhere past the cutoff of 1.660, so it's maybe somewhere about here. And that means that the results of this study are unusual and significant, and we would say that we reject the null hypothesis. Another approach is the p-value approach. And so to calculate the p-value, again, you can use a Casio or a TI graphing calculator. The steps are similar to the first example that we saw. For the Casio calculator, you want to take these steps and get to the 1s function. One difference here is that this is a right tail test, so now you want to make sure that your inequality for the alternative hypothesis is greater than. For the TI calculator, again, you want to navigate and get to the function called t-test. And again, you want to make sure that your alternative hypothesis inequality is in the right direction. So here it's in the greater than direction. And when you do that, ultimately the p-value comes out to 0.0292. So again, the meaning of this p-value is it's the probability that a random sample of 101 extra strength air fresheners would have a sample mean lifetime of 36.9 days or more and a sample standard deviation of 4.2 days, assuming that the null hypothesis is true. In other words, that the mean lifetime of extra strength air fresheners is just the same as the mean lifetime of standard air fresheners. And so the last thing is now we'll want to compare our p-value to the level of significance. Our p-value was 0.0292. The alpha is 0.05. This is less than 0.05. And that means that these studies' results are unusual and significant, and we'll say that we reject the null hypothesis. So we'll state the conclusion. In terms of the alternative hypothesis, we reject the null hypothesis, and that means that there is enough evidence in this study to support the alternative. So there is enough evidence to conclude that the mean lifetime of extra strength car air fresheners is greater than the mean lifetime of standard car air fresheners. We'll take a look at one more aspect to this problem. Just a note to this example. And this note has to do with statistical significance versus practical significance. In the example we just did, the results of the study were determined to be statistically significant, and for that reason, we determined that the evidence was sufficient to conclude that the mean lifetime of extra strength car air fresheners is greater than the mean lifetime of standard car air fresheners. Nevertheless, it's important to consider practical significance. The practical significance of the results of a study as well. So remember from example 2 that standard car air fresheners have a mean lifetime of 36.1 days. In the study done by the engineers, in their sample, they ended up with a mean lifetime of 36.9 days, only 0.8 days longer than the mean lifetime of standard car air fresheners. So there's no question that the results of their study were statistically significant, but the study's practical significance is open to interpretation. Would you consider it worthwhile to spend more money on an extra strength car air freshener that may last on average 0.8 of a day longer than the standard version?